Yeah, GeoGebra is the stuff. Okay, so examples of volume, namely using the disk method. So example one, find the volume of the solid formed by revolving the region bounded by y equals the square root of sine of x and the x-axis, namely from just 0 to pi, about the x-axis. Alrighty, so first of all, this is just a little basic pre-calc, hopefully, or trigonometry. Um, when x is equal to 0 and pi, we can plug it into this equation so that way we can figure out what points lies on the square root of sine of x curve, okay? So when x is equal to 0, y is equal to the square root of sine of 0. What is sine of 0? 0, right? So we get the square root of 0, which is 0. Now, if y is equal to the square root of sine of pi, what is sine of pi? 0. So this is going to be the square root of 0, which is 0. So this might not be helpful, right? But we need another value, another angle that can help us. You see, since we start from 0 and we're ending at pi and we're drawing a curve, that means that the values somehow increase and then decrease, okay? So I can choose another value for sine, for another angle, and evaluate it. What's a common angle do you think I want to use here between 0 and pi? 90 or pi over 2. What is sine of pi over 2? 1. Square root of 1 is 1. So I'm going to plot these 3 points and then make a quick sketch of this curve. All right. So here's my y-axis. Here's my x-axis. And we know that the graph is bounded by the x-axis. So by the way, just a little heads up, if the graph is bounded by the x-axis, that's exactly the same thing as saying y is equal to 0. Okay, so it's exactly here. There's your y equals 0. It's the x-axis. And we know that this is going to go from 0 to pi. So here's 0. Here was pi. Let's say somewhere here is pi over 2. And we can plot our points. So it was the origin, 0, 0. At pi over 2, we know that we're at 1. And at pi, we're back at 0. So between those 3 points, I can draw a curve. All right, so this suffice. This is going to be the curve of y equals the square root of sine of x. All right, so remember in this problem, it did say that our curve, square root of sine of x, is being rotated about the x-axis. So it's rotating this way. Okay. So what I'm going to do, since it's rotating about the x-axis, I'm going to try to show you what the image looks like, but I won't be able to do the full-blown 3D. So the idea here, or the technique to do, is since that is being rotated about the x-axis, is that you can reflect the square root of sine of x curve along the x-axis. Basically, it makes everything negative, right? So for example, at pi over 2, when we had 1, if you reflect that over the x-axis, then the y value will be what? If I reflect it over the x-axis, then the y value should be -1. There you go. So I'm just going to put this as a reference point. And now I'm just going to reflect this graph over this axis, right? So it should look like a curve, not a line. My bad, guys. So there you go. All right. So how do I solve this problem now? Well, first of all, we only have one curve, and it's our region, our main region, is being bounded by the curve and our axis. So in short, in plain English here, the simplest application of our disk method, which I'm going to use, involves just our plane region bounded by the graph of f or y and the x-axis. If the axis of revolution is the x-axis, then your radius is simply going to be the function, right? So in other words, if I drew this line segment here, this line segment would represent our radius for the disk. This is going to be my R, right? Because if I reflect this over here, if I reflect R over the x-axis, then I can create my, now, like I said, guys, disclaimer here, I can't do the 3D stuff, but I can show you on the plane region, and my disk is not going to come out nice. It's going to come out a little nasty here. So here's my disk. Okay. There you go. If you look at that list that I drew, I'm going to zoom in on it so you guys can really see it. The disc was drawn sort of like in a purple, not a purple, in the brownish color. You can see that its radius depends solely on the value of the square root of sine of x, right? So when I apply the disk formula here, by the way, that formula states that it's just volume V equals pi from A to B of R of x dx, where R of x is your radius of your disk. So we're going to get pi of, R of x squared, my apologies, of 0 to pi of the square root of sine of x squared dx. And this is actually an integral that we could compute real quickly. What is the square root of sine of x squared? How would you simplify that? Sine of x. So this is now going to equal to pi from 0 to pi of sine of x dx. Now, what is the antiderivative of sine of x? Say it louder. Negative cosine. So this is now going to equal to pi of negative cosine of x from 0 to pi. So you plug in your limits of integration here. What you're going to get is pi on the outside, right? Because that was our constant multiple. You will have negative of cosine of pi minus negative cosine, oops, my bad, of 0. Now, what's cosine of pi? 1. Well, no. Cosine of pi is not 1. Try again. -1. So this is a -1, but two negatives make a positive. So we're going to get, sorry, I'm going to bring it this way because I don't want to run into the other page. You'll have pi times negative of -1, which is 1. Now, what is cosine of 0? 1. There's a negative. There's two negatives in front of it, right? So those two negatives will be positive. So we're going to get pi times 1 plus 1, which gives us 2 pi. Yeah? No. Oh, you only change the limits of integration when you use a U sub. I could do an example of that after I do the washer method. All right. How's this first example? Pretty good. What's important to note is that if you just have a single function and the region is bounded by that function and the x-axis, then the radius is simply going to be your function. That's going to be your big R, because the radius of each disk depends on some value of x that you choose. Because when that value of x that you choose, when it hits your curve, you're able to create the radius. Okay, let's try it again. This one was a little tricky in terms of graphing. For number 2, we're not going to compute the area, compute the volume, but we're just going to set it up. So it says set up, but do not evaluate the integral, which equals the volume of the solid form by y equals the square root of x, y equals 0, x equals 16 about the x-axis. So in this problem, by the way, if we know that if x is equal to 0, y is equal to 0. But if x is equal to 16 in this problem, then what is the square root of 16? 4. So y is equal to 4. So I get my points essentially. One point got to be the origin, 0, 0. The other point is going to be 16, 4. And I'll just remember y equals 0. This part here of the problem is the x-axis. Okay. So let's make our graph. So sorry, that should have been x. So we're doing this from 0 to 4. So here's 0, the origin, 1, 2, 3, 4. No, I'm sorry, this should have went by. So sorry, the y value's got to go by 1. The x values, I could just make them go by 16s, 4s. So 4, 8, 12, 16. Y values, I'm going by 4s, 1s. So 1, 2, 3, 4. So here's our 2 points, the origin, and 16, 16, 4. So it should look like that. Now it's bounded also on the x-axis. All right. So, okay. So far we have our sketch done. And we're rotating now about the x-axis. Okay, so if I'm rotating about the x-axis, just think about that red curve reflects over the x-axis, okay? If you reflect that curve over the x-axis, the origin point will still stay the same, but when x is equal to 16, one additional point that you'll have now is -4. All right, so let's just say we chose some value of x, right? Let's just suppose I chose x was equal to 8. Right? If I'm rotating this about the x-axis here, at x equals 8, if I want to create the radius is going to be the distance between the x-axis and your curve. So here, from x equals 8, you can see that, okay, here's my radius. If I reflect this over now, the x-axis, the radius part, I can simply draw a disc. So r is not going to be 8, but r really depends on your function, which is square root of x. So from our sketch, we're now able to set up the volume problem. We say volume equals pi from a to b of r of x squared dx. The region is from 0 to 16 of the square root of x squared dx. And that's it. You can leave the problem alone. All right. But as you guys probably would know, what is the square root of x squared? It's just going to be x, right? But again, this problem never asks us to compute the area. You just set it up. The volume, you just set it up. So here were 2 examples using this, and I would like to do 2 more examples of washer, at least in the next video.